the MATH1241 exam, and you probably know that questions 1 and 2 of the MATH1241 exam are the same as questions 1 and 2 on the 1231 exam. So you probably want to check out the Wednesday stream of the 1231 exam, and Daniel and Jonathan also had some general sort of exam hints as well.
Yeah, they sort of introduced what you have to do in an exam, making sure you do everything in separate books and all that. So have a look at the start of that and then look through the first couple of questions.
Yeah, but we're here to do I'll do question 3, John will do question 4, and we'll get going,
okay,
I think.
Okay,
thanks, John. All right, so first part of question 3 says, let A be this 2 by 2 matrix using 9, minus 1, 4, 5. We need to find all the eigenvalues and eigenvectors and explain carefully why A is not diagonalizable. And this was just the name of the exam. I thought I should put it somewhere. Okay, so let's do that. First, of course, we calculate the characteristic polynomial of the matrix. So the characteristic polynomial is, let's call it P of lambda. It's the determinant of A minus lambda I. So we just take the determinant of 9 minus lambda minus 1, 4, 5 minus lambda, and we get 9 minus lambda, 5 minus lambda, plus 4, and when you unscramble all of this, you've got lambda squared minus 14, lambda plus 49, and this is actually lambda minus 7 squared. Okay, I'm going to step inside that little calculation to point out that obviously this means that lambda equals 7 is a repeated eigenvalue of A. Is the only eigenvalue of A. So to find all the eigenvectors, we need to look at the kernel of A minus 7i. I might do this down here. So subtracting 7 from the diagonal elements of this matrix, we're looking for the kernel of 2 minus 1, 4 minus 2. And because the row operations preserve the kernel, this is the kernel of 2 minus 1, 0, 0. And we can see that there's one leading column. This is going to be one non-leading column. It's going to be a one-dimensional kernel. And when you figure out what you need, it's the span of, let's say, the vector 1, 2. Okay? So the kernel is the span of, it's a one-dimensional space spanned by 1, 2, and the eigenvectors are just every non-zero vector in this span. So we might answer the eigenvectors of A for lambda equals 7 are all the constant multiples of 1, 2, except your constant must be non-zero. 0 is never an eigenvector. Okay, and that answers part A. How much room have I got? Still got some room. The reason why A is not diagonalizable means you have a basis consisting of eigenvectors, a basis of R2 in this case, consisting of eigenvectors of A. But all the eigenvectors span a one-dimensional space, not 2. So you just don't have enough linearly independent eigenvectors. So let's write something like this. A is not diagonalizable as all eigenvectors span a one-dimensional space. Not R2. Okay, so there's no basis for R2 consisting of eigenvectors of A. Maybe let's write that down. There is no basis for R2 consisting of eigenvectors of A. Okay, so we're going to clean the board, change this, and get on with the next part. Oh, sorry. I just knocked something very important. I think it was the microphone. All right, you notice that Wednesday's live stream had a high-tech green screen. We're not that high-tech, or not that organised. One of the two. Okay. So we've got a two-person system for cleaning this board. Thank you. All right, while that's drying off, you can be reading the next part of this question, which says, so I've just reminded you, this wasn't on the exam, this extra reminder, but just to remind you what the matrix looks like, we have to now find the matrix of the linear map, which represents multiplication by A. So it's a map T from R2 to R2. T of X is just AX. In the exam, they use X with an arrow over the top, but I always write X underlined, so I've just done that here. We need the matrix of this map with respect to a particular ordered basis, V1, V2, which we use in both the domain and the codomain. V1 is 1, 2, and V2 is the vector V3. Now you should look at this for a second. You go, hang on a minute. V1 is 1, 2. That's an eigenvector. We just proved this is an eigenvector with eigenvalue 7. So that's going to make our task a bit easier. And what we want to use to answer this question is the general matrix representation theorem. By the general matrix representation theorem, we have a recipe for finding this matrix. Let's call it M. M. Okay. So to get the first column, you apply T to V1, right? That gives you an element in R2, but we need its coordinate vector with respect to the basis B. And that's the first column of the matrix of T with respect to this particular basis. And for the second column, obviously, you do the same thing with respect to the second basis vector, V2, all right? So we just have to calculate these two vectors and take their coordinate vector with respect to B. So let's start on that. We know that T of V1 is just 7 times V1, as V1, which is 1, 2, is an eigenvector. Okay, we proved that in part 1. Next, let's just say when you take the coordinate vector of 7 times V1 with respect to the basis B, it's saying that this vector, T of V1, is 7 times V1 plus 0 times V2, so the coordinate vector is just 7, 0, okay? And that's going to be the first column of this matrix. Next, for V2. T of V2, you just calculate it. So you're multiplying it by A. So here's A, and V2 is 2, 3. 18 minus 3 is 15. 8 plus 15 is 23. So we get this vector, and now we need to find the coordinate vector of this vector with respect to the basis V1, V2. So we need to form a little system of linear equations and solve it. I'll do that over here. So we put V1 in the first column. Whoops, that's a 2. V2 in the second column, and the right hand side is the vector we're solving for, which is 15, 23. And you'll have to do these calculations, so we'll do them here, we'll just whiz through. The second row, you probably want to delete twice, subtract twice the first row from it, and you'll get 1, 2, 15, 0, 3 minus 4 is minus 1, and 23 minus 30 is minus 7. Okay, and one more step. I'll leave that. We could multiply through by minus 1, but we can just leave it and add twice row 2 to row 1. So row 1 becomes row 1 plus 2 row 2 to make the, or you could back substitute. I prefer doing it this way. So we'll get 1, 0, 15 minus 14 is 1, and 0 minus 1 minus 7. So the solution is the first constant is 1 and the second constant is 7. So we conclude that t of v2, its coordinate vector with respect to the basis b, which is the coordinate vector of 15, 23, with respect to the basis b, is just 1, 7. And therefore the matrix M that we're looking for has these columns, 7, 0, and 1, 7. Okay, that's the answer for that part. Remember, the normal matrix representation theorem looks at maps from Rm to Rn with respect to standard bases, and for anything else you need the general matrix representation theorem. All right, on to the next question, sub-question. Okay, talk amongst yourselves. Try and get rid of some bubbles. In some universities, in lectures, they employ people to rush in and clean the whiteboard or the blackboard after the lecturer has finished with it. That would be pretty cool. But John and I have to do this ourselves. That's fine. Okay, so this is a theoretical, or quite an abstract theoretical linear algebra type question about linear maps. So V and W are vector spaces, presumably over the same field, that's not specified. And T goes from V to W is a linear map. We're also given M vectors in the vector space, V1 up to Vm, okay? Now the first part says, prove that if, once you apply the map T to these vectors, so T of V1 up to T of Vm, if those vectors are linearly independent, then the vectors that you started with must also be linearly independent, okay? And the second part of the question, if you look at the actual exam paper, it spells it out, but it's really asking, is the converse of A true? Which means if the vectors V1 up to Vm are linearly independent, is it true that their images are also linearly independent? Okay, so we'll come to that after we've done part A. So this is just a nice proof where we assume this, and we want to show that V1 up to Vm is linearly independent. Or the set of those is linearly independent. Okay, so let's start by writing down our assumptions. So we're supposing that T of V1 up to T of Vm, these vectors are linearly independent. I think it's worth writing that down so that you tell everyone you know that you can use this information. But now we want to show that these guys are linearly independent, so you take an arbitrary linear combination of them and set it to 0, okay? Then suppose that lambda 1 v1 plus lambda 2 v2 up to lambda m vm is the 0 vector for some scalars lambda 1 up to lambda m, okay? And what we need to show is that this is the only solution is the trivial solution where lambda 1 up to lambda m are all 0. So what can we do? Well, really all we can do is apply the map T to both sides. So T of 0, I'm going to work backwards. If you apply T, a linear map, to the 0 vector of V, you're going to get the 0 vector of W. That's a fact for all linear maps. So we can have 0 is T of 0, and that's applying T to the right-hand side. Now we apply T to the left-hand side. Lambda 1 V1, lambda 2 V2, blah, 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 up to lambda M Vm. And of course the point is that T is linear. So we know what it does to a linear combination of vectors. It gives a linear combination of T of those vectors. So this is lambda 1 T of V1 plus lambda 2 T of V2. And you can start to see why this is helpful. So this is as T is linear. And then you see, what have we got? We've got a linear combination of m vectors that we know are linearly independent. So the only solution is that all of these scalars must be 0. So full stop here, since T of V1 up to T of Vm are linearly independent, this is where we use that assumption, we conclude that actually all the scalars, lambda 1 up to lambda 2, lambda 3, all of them up to lambda m, they're all equal to 0. And this is what you need. Maybe full stop. Therefore, we've succeeded in what we're trying to do, which is to show V1 up to Vm are linearly independent. Okay, so we may as well write that down. We know that we've done the job. Okay, and that was a nice proof, so I think we can use the QED symbol there. Good. So we can't suddenly become linearly independent when we're not. We have to start with something linearly independent if, once we apply T, we get something linearly independent. Is the converse true? What does that mean? If these vectors are linearly independent, does it imply that their images are linearly independent? Have to think about it for a second, and hopefully you'll see that the answer is no. This is actually false. So let's start this down here. No. So we're trying to prove something is false. We want to come up with a counterexample, and there's many different ways you could do this. Let's say, for example, and it's just enough to come up with one specific counterexample. So let's take V equals W equals R2, so a map from R2 to R2. We'll take vectors V1 and V2 to be the standard basis vectors, 1, 0, and V2 to be 0, 1. And we'll map everything in R2 to 0. This is a linear map. It's a kind of boring linear map, but every vector is going to map to 0, and therefore T of V1 and T of V2 will definitely not be linearly independent. So, and define T goes from R2 into R2 by T of V is equal to 0 for all V. So it's multiplication by the 0 matrix, which is how you know that it's linear. So let's just say then T is linear. We know that V1 and V2 are linearly independent. Okay, but T of V1 equals T of V2 equals 0. And any set containing the 0 vector is not linearly independent. This one has it twice. So that's the bad side of the pen. Let's use this pen. So the punchline is that T of V1 and T of V2 are linearly dependent. Okay? So you just give some example to show that this is not always true. There's lots of different choices. In fact, you could say this is overkill. This really is overkill. You could also project from R2 onto a line, right? Project onto your favorite line. Then the image of any vector is on the line. And so they aren't linearly independent if you have two different vectors on the line. Okay, so that I think is enough for this part 2. And we'll do the thing. All right. Okay, have a read of this. This is something quite different. Okay. What is going on in this question? Thank you, John. So while the board dries, this is the weird subpart, I would say, of this exam. So everything we do normally in linear algebra is been over the reals or the complex numbers, but we do say in lectures that you can use other fields as well, including finite fields. And in lectures last year, they went over an example somewhat like this, and then it was on the exam. Okay. So we also did something on finite fields this year in lectures. This question involves the field with 4 elements, and the elements we're going to denote by, you need 0 and 1 in any field, and you also have 2 more elements called alpha and beta. And then we give you the addition and multiplication tables, and it's worth sort of absorbing these for a while. So what's going on? When you add 0 to anything, obviously nothing happens, that's fine. If you add 1 to 0, you know, that's obvious. If you add 1 to itself, you get 0. Actually, if you add anything to itself, you get 0. So 2 times x is 0 in this field for any x. Alpha plus 1 is beta, and beta plus 1 is alpha, and that's symmetric. So let's make a note of that, because we'll need that a few times. Alpha plus 1 is beta, 2x is 0 for all x in this field. That's sort of all you need to know, really. Multiplication, multiplying by 0 does the usual thing. Multiplying by 1 does the usual thing. Alpha squared is beta, alpha beta is 1, and beta squared is alpha. So those are the other things that we'll make a note of. Alpha squared is beta, beta squared is alpha, and alpha beta is 1. So I guess alpha is the inverse of, multiplicative inverse of beta and vice versa. So the first thing you need to do in this question is kind of absorb the information in these tables and extract the stuff we're going to need, as you'll see. There's going to be 2 tasks in this question. In fact, I should tell you what the next bit is. It's on a different page, but there's also, in the question, it defines another vector, v, which is alpha 0, 0. Because, you know, in row reduction questions, it really helps to read the whole thing before you answer, because you may be able to answer 2 parts at the same time. I'll have to tell you what's on the second piece of paper, which is to find the coordinate vector of v with respect to this ordered basis. No, it's okay. So first thing we need to do is show this is a basis, and the second thing, actually the third thing will be to find the coordinate vector of v with respect to these guys, which means that when we set up the row reduction, which is completely normal row reduction except that you're doing all your operations in this field of 4 elements, we can just stick this new vector v on the right hand side because we'll need it for part C of this question. Okay, so let's go. We want to show that this is a basis for F3, and actually I wonder if we can use a dimension argument. I mean, normally R3 has dimension 3, and I think, well, let's just not do that. So set up a row reduction. You might need to prove that first, so let's not bother. We'll just prove that this set B1, B2, B3 is linearly independent and spans. Okay, so we need the vectors from B1, 1 alpha beta, beta 1 1, 1 0 alpha, and because I know what's coming, I'm also going to put the right hand side alpha 0 0, which we don't need for part A, but just to save us repeating the work, okay? And just as in a normal row reduction, we want to clear this first column. So we're going to subtract alpha times row 1 from row 2, and we're going to subtract beta times row 1 from row 3. Okay, so row 2 becomes row 2 minus alpha row 1. Row 3 becomes row 3 minus beta row 1. How do you do that? Well, we could just write down the first row. Okay, and we've designed these operations to put a 0 in the rest of the first column. And we'll do some calculations over on the side. So here we've got 1 minus alpha beta is what's going to appear here. 1 minus alpha beta is 1. Okay, that's alpha beta here, that 1. So this is 1 minus 1, which is just 0. So this is actually going to be 0. Not sure why I wrote that in red. Never mind. Here, 1 minus beta squared. Okay, 1 minus beta times this entry, so beta squared. And beta squared is alpha, it's 1 minus alpha. This 2x equals 0 tells us that minus x is the same as x. Okay, so subtracting is the same as adding in this field. We say it's got characteristic 2. So this boils down to 1 plus alpha, which is beta. Okay, whoops, I stood on the lights. Never mind. So beta is what we get in the bottom of the second column, like that. And we keep going in this manner. So this is 0 minus alpha times 1. So 0 minus alpha is the same as 0 plus alpha. That's just going to be alpha. Alpha minus beta times 1 is alpha minus beta, which is alpha plus beta, which is, oh, I didn't write that up. Alpha plus beta is 1. So you get that from here as well. Just from throwing things on the other side and remembering that addition is the same as subtraction. Alpha plus beta is 1. Okay. And I forgot to do these elements on the right hand side here. So 0 minus alpha squared is the same as alpha squared, and alpha squared is beta. So we'll get a beta here. 0 minus alpha times beta is the same as alpha beta, which is 1. So after you do your careful row reduction using these row and column, after one step you get this. Okay? And they've been quite nice to us because there's a 0 here, so let's just swap rows 2 and 3, and that will sort things out for us and put us into row echelon form. So that's a relief, perhaps, or, you know, why can't we do more fun row reduction in this field? Might be another response. Okay, so it looks like this: 0 0 alpha beta, 0 beta, 1 1 1 1. Yeah. Okay, and this is in row echelon form. And we know that when we hit row echelon form, we can start to make decisions. So we can answer this question now, is it a basis? We see that every column is leading and there are no 0 rows. So what does that tell us? Since there are no 0 rows, or the row echelon form has no 0 rows, that means there's always a solution. The set B1, B2, B3 spans F3. It's a spanning set. Okay, it's always got a solution for any right-hand side. And since there's no non-leading columns, the solution is always unique, so it's linearly independent. So you give some argument along these lines. No non-leading columns, the set is linearly independent. And that means it's a basis. The set is a basis. Okay. And I guess this also shows that F3 has dimension 3, which is what we would expect. Now I'm going to have to store some information, and maybe we'll just clean this because I'll need this for part C. So I'm going to transcribe this over here and then we'll just clean that. Okay, so I'm just going to store this here. We had 1 beta 1 alpha, 0 beta 1 1, 0 0 alpha beta. We'll just need that later, but now we could clean this up. Thanks, John. Okay, what else do they want us to do with this setup? Oh, and can you keep the, just from A down? Yes, yeah. Thank you. That would have been a disaster. Okay. Good. Okay, that's more or less all right, hopefully. Slightly over the top of that vector, but I think we can see what we need to see. So you can have a read of what we have to do next. That's fine, thank you. Okay, we appreciate a nice shiny whiteboard in this room, so try to make it nice. Okay, the next question has, the next part B, has nothing to do with the fact that we're working in this strange field, really. You just have, we had a set of vectors B1, B2, B3 before, which we just showed was a basis for F3, and now we've got a slightly different set, B1 plus B2, B2 plus B3 and B3, and we ask you to explain why it's spanning but not a basis. Okay, and maybe we could take the second part of that first. Why do we think this is not a basis? Well, there's too many vectors, right? So part of what we learned in the previous part was that dimension of F3 is 3. We have 4 vectors, so it can't be linearly independent. Let's write that down. Okay, from part A, we have that the dimension of this vector space F3 is obviously 3. But this new set contains 4 vectors, and 4 is obviously bigger than 3. So these 4 vectors are not linearly independent. Okay, there's too many of them, and hence they're not a basis. Right, but to show that they're spanning, we know that any vector can be written as a linear combination of B1, B2, B3, because that set is a basis, B1, B2 and B3. We've already got B1 and B3 in our set. So it's enough to show that we can extract B2 from this information. So let's say, to see why the set is spanning, note that the vector B2 we had before can be easily obtained from this set. So for example, it's B1 plus B2, take away B1, which we've got. So every vector in R3 can be expressed as a linear combination of B1, B2, B3, as it's a basis, as this is a basis, and hence, this is too long for me to do part C on this same board, and hence, as a linear combination oh no, maybe I can, of B1, B1 plus B2, B2 plus B3, and B3. Okay, is there a question? F3, what have I put?
R3.
Where? Oh yes, I did, thank you very much. See this R? That's not an R. Let's just change it into an F, thank you, Josh. All right, F3, thanks. We don't know what this, well, we do know what the field is. It's that funny field of 4 elements, but this sort of thing would be true anywhere, okay? So if you can write it as alpha 1 B1 plus alpha 2 B2 plus alpha 3 B3, then you can use this substitution to get a linear combination of these vectors. So that's all we need to do to answer part B, okay? And now, unfortunately, I think I haven't left myself enough room, so we'll have to clean this again, sorry. But yeah, so yeah, everything from the note down, thank you, sorry. While that's happening, part C we can see is what we sort of foreshadowed at the start. It's just to find the coordinate vector of this vector V with respect to the ordered basis. And in the exam question, V was introduced at the very start together with B1, B2, B3, so it's not like a big shock when you read part C that suddenly you have to go back and do these calculations again. I just didn't write it on the slides that way to save a bit of space. So we're just going to do a standard row reduction here.
I should say there'd be no problem, by the way, if in the exam you actually did part A, then part C, then part B. You don't care which order you do them, as long as they're all in the right order.
Yeah, you can mix up the order, and of course you can do the calculations twice if you really want to. I'm just trying to help you. We're just trying to help you save some time, okay, and possible frustration. Saving time is a good thing for everyone. Okay, so part C of this question about F3. More row reduction, please. So, I wonder, yeah, it's still wet. Okay, might talk about, remember we started with B1, I'll just have to remind you what we already did to get to that matrix there. So, we'll just say something like, from part A, so this is an answer to part C now. So from part A, we saw that, when we put B1, B2, B3, and then V into a matrix and we row reduced, it has a row echelon form, which is the thing we stored over there, which I'm going to copy now, and then we'll continue. 1 beta 1 alpha, 0 beta 1 1, 0 0 alpha beta. Okay, so we already got this far in the row reduction. You could stop here and row reduce. I just like going to reduced row echelon form, so I'm going to keep going. So I'd like a 1 to appear here, and we know that alpha beta is 1, so I'm going to multiply row 3 by beta, and at the same time, look at what we've got up here. I can get rid of this beta and 1 by subtracting row 2 from row 1, and that doesn't interfere with this, so I'm going to do those at the same time. So row 3 will become beta, oh, what a mess, beta row 3 to get a 1 here, and at the same time I can clean row 1 up a lot, they're being nice to us, by subtracting row 2, which is the same as adding row 2 in this field. So that'll give us 1, 0, 0, and then alpha plus 1, which is beta. Okay, row 2 is unchanged, and this becomes 0, 0, a 1 here because alpha beta is 1, and beta squared on the right hand side, which is alpha. Okay, so now all we have to do is fix up row 2, and I'm going to first subtract row 3 from row 2 to get rid of this 1, and then deal with the diagonal element. So row 2 becomes row 2 minus row 1. As I say, you could stop and back substitute at any time. I just kind of like reduced row echelon forms. 0, beta, 0, and then this will be 1 minus alpha. No, hang on, what do we do? Yeah, 1 minus alpha, which is the same as 1 plus alpha, which is beta. That's nice. And 0, 0, 1 at the bottom, which is alpha. And so you can see you kind of want to divide by beta, but we don't talk about dividing by beta in this sort of finite field. We're going to multiply by alpha, its multiplicative inverse, to get a 1 here. So the final step is row 2 becomes alpha row 2. And that'll give me the reduced row echelon form, which has the identity matrix on the left because it's a basis. This becomes 1 and 0, 0, 1 alpha. And this is the coordinate vector of V to answer the question. So the coordinate vector of the vector V with respect to the ordered basis blah B1, B2, B3, or if you're in a hurry, the given ordered basis is this vector that we found, beta 1 alpha. Okay? And you can actually check if you've got time. You can form beta times B1 plus B2 plus alpha times B3, and you will get the vector V that we started with here, alpha 0, 0. Okay, cool. Now that's the end of question part 3, and it's the end of the linear algebra part. And the final part of this question is probability stuff. Thank you, John. Okay, so start having a read of this. Oh, that's gone all sticky. Start again. Okay. Oh man, I do not want to do that. This is good television, this is live streaming at its best. Okay, let's say that's adequate. Okay, good, and I'll dry the board. Thank you, okay. Malfunction. So this is so far fairly standard things that you're being asked to do. Find the mean and have a look at the variance. It's a continuous random variable x with a given density function, but a little bit, well, continuous thing, we're going to have to integrate this, and we have to show that it doesn't have a finite variance. So the variance is going to be infinite, which is an interesting sort of random variable. Let us begin. Okay. So the density, if x is less than 1, it's 0, so the smallest value you can have is 1. And for x greater than or equal to 1, the probability density function is some constant c divided by x times 1 plus x squared, and the value of c is given, 2 on log 2. And the exam question says you do not need to prove that this is a density, so you just assume that this integrates to 1 with this value of c, okay? We're not asking you to check or prove that. Just take that as given. Indeed, I have not checked or proved that. I just trust them. All right, but we do want to find the mean of x. And we know how to do that. So the mean of this random variable x is, well, it's called e of x, it has a name, and it's the integral from, this is the general formula, minus infinity to infinity of the value x times the density at x with respect to x, okay? And now we substitute the particular value of f of x, which is 0 below 1. So really we're integrating from 1 to infinity x times this thing, c over x 1 plus x squared dx. And as you can see, the x is going to cancel. So I could have written it down like this straight away. It's c over 1 plus x squared dx. And we know the value of c. Now, you guys probably recognise this, and you probably know what this is. I usually ask someone, or look at Maple, or you also have this sort of beautiful standard table of basic integrals here, and it's one of your integrals. So the integral with respect to x of a squared plus x squared, it's a arctan. Okay, so this we can write down because we know that integral. So it's actually c tan inverse of x, and we're evaluating it at 1 and infinity. And really this is a limit, but you guys know how to do this. So the limit at infinity is pi on 2, and the value at 1 is pi on 4, because pi on 4 is the place where cos equals sine, right? So this is c times pi on 4, and c is 2 log 2. So this is going to be, 2 on log 2 times pi over 4. You end up with the answer pi over 2 log 2. Okay, that's a 2. Pi on 2 log 2. So that's the mean, pi over 2 log 2, since it looks a bit yucky. Okay, it's just a calculation and checking that you know the formula. I'll try and do the variance sort of in the same place. So for the variance, first we calculate the expected value of x squared, and then we subtract the square of this mean, which is a finite value. So the variance will be infinite if the expected value of x squared is infinite. So what is the expected value of x squared? That is the integral from minus infinity to infinity of x squared f of x dx in general. And then for us, when you substitute what f is, we're integrating from 1 to infinity cx squared over x 1 plus x squared dx. And obviously you get cancellation, so let's just pretend I never wrote that x squared, I never wrote that x. We're integrating this thing. And for this, we need partial fractions to sort out this integrand. Oh no, we don't. Sorry, we don't need that at all. I'm thinking too far ahead. This I can do with a substitution. Right. So we're going to just come over here and let y be the denominator, 1 plus x squared. And then dy dx is 2x. And so we can continue with this integral. Maybe over here. The expected value of x squared is, the c can come out the front, and I'm going to have to divide by 2 because dx is dy over 2. Pretend I said that first. Dx is dy over 2, and this thing happens. The expected value of x squared is c over 2, the integral of 0 to infinity dy over y. Right? Sorry? 1 to infinity, that's just as well, isn't it? Thank you, John. 1 to infinity. We don't like 0 on the denominator. And so this is log, right? I know this one. So this is c over 2 log y, and we're kind of evaluating it between 0 and infinity, which is obviously, that's a limit here. And the point is, the limit is infinite. So let's just say which is infinite.
Should be x dx is 2 dy over 2.
Say that again.
X dx is dy over 2.
X dx. Oh.
Yeah, the interval, right?
Pretend I didn't write that down. It's just this. Okay. Okay. Shall I fix it?
No, leave it.
I'll fix it in red. I do have 2 calculus experts. I prefer summation, discrete maths, but that's fine. x dx is dy over 2, and that's what we did. Liking that? But there's a y. You have to have a y.
It doesn't matter. It doesn't make any difference because the end result's
I think you're steering me down the wrong channel. This is correct, right? So, oh, x dx. No, I see what you're saying. X dx is dy on 2. Yeah, it's this. You guys can do this better than me. It's fine. The point is, you get here, and it's infinite. And if the second moment, ex squared, is infinite, then the variance is also infinite. So therefore, the variance of x, don't forget to come back and talk about the variance, it's the expected value of x squared minus the expected value of x squared. This is also infinite, since the expected value is finite. Okay. If you had the right infinity that you were subtracting, you might be able to cancel it, but there's no chance here. So the variance is infinite, which is what we were asked to prove. Okay? Great. So that's part B, and there's one more subpart to this, question 3. Excellent. Okay, so have a read. Ooh, I did it again. The red part is just transcribing the density from the previous piece of paper. Okay. And of course they weren't steering me wrong. These guys know what they're talking about. Who let the discrete mathematician do the integration question? Okay. So now we have to do something with the median, which is a little bit unusual, but we tell you here the definition of median. It's the real number such that the probability that your random variable is less than or equal to m is exactly a half. So you're integrating the density from minus infinity up to m, and the value should be a half. Okay, that's the median. You're asked to prove that the median is bigger, strictly bigger than a particular value, right? So what does that mean? That means if you integrate from minus infinity up to this value that we're given, this tan of pi plus log n all divided by 4, you're not at the median yet. The median is bigger, and that means you haven't reached a half yet when you integrate, right? So we have to show that the integral up to this value is strictly less than a half, and that will do the job. Okay, so let's do that. I'm going to call this thing m0 because it's a bit of a mouthful. Feel free to define notation that if it makes your life easier. So m0 is tan of pi plus log 2 over 4. Okay, and we can see tan there, and we had arctan before in the expected value, so it'd be nice if we could get those two to come together. And we must show, we want to prove, that the integral from minus infinity up to this value, m0, of f of x dx is strictly less than a half. It's because this is the probability that x is less than or equal to m0. Okay? And that will tell you that you haven't got to the median yet. So this implies that m0 is strictly less than the median, which is what we're after. Okay, so we just have to do this integration. And we don't need to evaluate it precisely. It would be enough to get an upper bound, which is still strictly less than a half. Okay? So the integral from minus infinity to m0 of f of x dx, again, is the integral from 1 to m0 of the density cx 1 plus x squared dx. And I don't really like this x here. It makes my life difficult, and as I sort of said before, you can try to think about partial fractions and stuff, but here we could use the fact that we can be a bit sloppy. We only need an upper bound, and everywhere that we're integrating, this x is greater than or equal to 1, and it's in the denominator. So if we leave it out, we'll be integrating something that's bigger, strictly bigger in fact, and that's fine for an upper bound. So because m0 is strictly bigger than 1, I assume this is strictly less than the integral from 1 to m0 of this c over 1 plus x squared dx. And this we recognise, we used it before, this integral is inverse tan. Okay, so it's c times tan inverse of x evaluated at m0 and subtract the value at 1, and this inequality, I'll explain it now, since x is greater than or equal to 1 throughout region of integration, with equality only at x equals 1. So as long as we go a bit beyond x equals 1, we'll get a strict inequality here. And now let's figure out what this is by plugging in the value of m0, and I'll do that over here. So this equals c times tan inverse of m0, right, minus tan inverse of 1, which we saw before was pi on 4. And it's the inverse tan of the tan of something, which is lucky. So that value there will just come out. You get c times pi over 4 plus log 2 over 4, just writing the operand of this tan thing, the angle, as a sum, because we have to subtract pi on 4. Okay, and so all you're left with is c times log 2 over 4, which is precisely 2 over log 2 over 4, which is a half, and that's as required. So as long as we're happy that this inequality is strict, you do get this being strictly less than a half, which would do the job. Does any calculus expert in the room, is it kind of immediately obvious why this value m0, what's the value I'd like this to be bigger than 1?
Tan of pi on 4 is 1, isn't it?
Tan of pi on 4 is 1, yep. And this is?
Bigger than
Tan of an angle bigger than pi on 4, so it must be bigger than 1, because tan's an increasing function.
Tan's an increasing function, ladies and gentlemen. So note, thank you. I think we should add this just to explain why we know we've got some actual weight in here that we're integrating. Tan of 4 is equal to 1, and tan is increasing. So m0 is strictly bigger than 1, and that's why I get this strict inequality here. Okay, and that's question 3. Thanks very much. I'll hand over we're going to clean the board, and then John will take over. Cool. All right. Dispose of that.
Thank you.
All right. Okay. May I just move this slightly? Okay. Good-o.
Is that too far over? Good, we can see it. Okay, so moving on to question 4, which is the calculus part of the MATH1241 exam. 1241 exam, I should say. So our first question here is about finding a reduction formula. Now, it's very similar to one of the ones we covered in lectures. We covered tan in lectures, if I remember properly. So this is cot. And we're asked to find a reduction formula and use it as an application to find this integral, particularly definite integral, cot to the 4n. And we're given these two bits of information. I've put them in blue because they come after the question. It's sort of free information to help us as a reminder, and in a way a bit of a hint, because it tells us there's a link between the square of the cotangent and its derivative. So this tells us what we want to do in the first step, which is basically to write cot nx, assuming n is bigger than or equal to 2, as cot to the n minus 2 times cot squared, and replace the cot squared with cosec squared minus 1. So that's what we'll do. Now we're going to begin by giving this integral a name, a convenient name. So we'll say, let's let in be this integral from pi on 4, pi on 2, cot to the nx dx. Let's say I'm going to split this up. Integral from pi on 4 to pi on 2, cot to the n minus 2x times cot squared x dx. You might feel like missing this step out, doesn't matter too much. I replace this cot squared here with, it'll be cosec squared minus 1. Okay, now this first part here, cot to the n minus 2 times cosec squared, is now cot to the n minus 2 times the derivative of cot. So we can use a simple substitute for cot, and do this part, whereas this bit here is the same integral from pi on 4 to pi on 2, but cot to the n minus 2. So it's 2 steps down on the same integral. So, well, we can do both steps together, why not? Well, it's probably a good idea to do a formal substitution here rather than try and do it all in your head. If you let u be cot x du dx is from what we've got over there minus cos squared x dx, particularly because we've got this extra minus sign to bother about. And we're going from pi on 4, well, cot of pi on 4, cot is 1 upon tan, so cot of pi on 4 is 1 on 1. And cot of pi on 2 is actually 0. Right? It's better to think in that sense of cot as being cos over sine, right? Rather than 1 over tan, so we don't get involved in that. So what we're going to get here is pi on 4 is from 1, the pi on 2 is 0. This is my u to the n minus 2 times cosec squared. Well, actually it's minus du, of course. So that's going to allow us to flip that limit over, minus the next term down, I n minus 2. This is what we mean by reduction formula, an integral in terms of, with a parameter in it, here an integer, in terms of the same integral but with a smaller parameter. So what do we get here? This is going to integral from 0 to 1 of u to the n minus 2. Put it in here. Integral 0 to 1 u to the n minus 2 du minus I n minus 2. The integral of 0 to 1 of u to the power is easy enough, you just add 1. So we're going to get our reduction formula 1 upon n minus 1 minus I n minus 2. And that's my reduction formula. Let's put I in on this side, shall we? I was going to put it in a box, doesn't matter. Okay. Now, if we're actually making use of this as a reduction formula, we'll need initial cases, I0 and I1, because we're stepping down 2 in each at each turn. We got cot to the 4, so we're going to write cot to the 4 in terms of cot squared, and then we cot to the 0. So for the last part of it, we only really need cot to the 0. Well, that's easy enough. The integral from pi on 4 to pi on 2 cot to the power 0x dx, but that's just integrating 1 from pi on 2 to pi on 4, and just get pi on 4. And It's not quite clear from the question whether we actually expect you to write down the cot, the n equals 1 case, but cot is actually on the integral table, so it's not a difficult thing to write down. That's I0, I1 is the integral from pi on 4 to pi on 2 cot x dx. Well, cot is log of sine, isn't it? Pi on 4, pi on 2. Well, sine of pi on 2 is 1, so log of 1 is 0, so that's going to be 0. Sine of pi on 4 is log of sine of pi on 4 is log of 1 upon root 2. So it's actually minus log 1 upon root 2, so that's just log root 2. So this thing would in fact be log root 2, half log 2 if you prefer. Okay, so that's our I0 and I1, our initial cases. Okay. As I say, we don't need I1 for the example we've got. We want I4, so let me just put this over here. I4 is going to be 1 upon 3 minus I2, which is 1 upon 3 minus, well, we just use the same formula again, of course, 1 upon 1 minus I0. So we're going to have I0, which we worked out over there was pi on 4, plus, well, a third minus 1 is minus 2/3, so we get pi on 4 minus 2/3, which is exactly what we were supposed to get. Okay, so that's our reduction formula. So we've not needed I1, but I've put it in here anyway, and why not? It's not as if it's been not that much effort. Okay, so we'll just clean the board and then move on to the next one.
All right. Like it's been a change of government or something. Now I'm your minion.
So in this question we're doing a differential equation by substitution. And this is something that's not in the ordinary level course, remember, it's in the higher level course. But as promised, we give you the substitution. We don't expect you to find one, not in this course. And in this case the substitution is, well, you can see what it is. We're using substitution, putting v equals y to the 3/2, and to solve this differential equation here, which otherwise we couldn't solve. And x times y to the half dy dx plus 2y to the 3/2 is e to the x cubed. Now, we really want, of course, to substitute in for dy dx. We could use the chain rule and differentiate this and get dv dx is equal to something. I usually find it easier to rewrite that as y equals something involving v. I was tempted when I first tried to do this to write that as v squared is y cubed and differentiate that. That didn't help. So what we'll do instead, we'll just do what I suggested earlier. As we have y is v to the 2/3, dy dx, the next there is going to be 2/3 v to the minus 1/3 dv dx. Now, for those of you who might be worried about am I allowed to take these cube roots and squares and all the rest of it, remember the dirty little secret about doing differential equations is basically you ignore such algebraic niceties and just get on with the job. And then, if necessary, check that it solves the dE at the end. So this now allows us to just substitute straight into the differential equation. So substituting the dE is, well, x times y to the half. Well, y to the half will be v to the 3rd. dy dx, we've already said over here, is 2/3 v to the minus 1/3 dv dx plus twice, or y to the 3/2 fact is just v equals, and the other side won't be changed to e to the x cubed. Okay. And the v to the third and the v to the minus third cancel themselves off, and what we've got here is a linear differential equation. The whole purpose of these substitutions is to turn a differential equation you can't do into one you can, and there's a linear DE that we know and we have a technique to solve. Hopefully you can all see that. So you just cancel the v thirds out. Now, we want it in standard form. Remember, the technique for solving a linear DE is to multiply through by an integrating factor, a factor that will make the left-hand side a complete derivative. And in this case, well, I said we want the standard form. So we're dividing through by x and the 2 and multiplying through by 3 and so on. What we're going to get dv dx plus, it would be 3 over x times v is whatever we're going to get here, 3 over 2x e to the x cubed. Right. That's right, yep. I've left my notes behind, let me just double check. Right. Always a good idea to have a double check of this before you go any further. That's what I got last time, so we'll assume that I'm right. So the integrating factor, remember, is going to be e to the integral of the thing multiplying v here. So we solve by integrating factor. Let's put the integrating factor over here. Is e to the, well, I'm going to write that as x of, because it's just more convenient to write things as x of when you're doing this. The integral of 3 over x dx. Well, that's just 3 times log x. So that's e to the 3 log x. Remember, we don't bother with an arbitrary constant in this part of the integral. It would just multiply everything through by a constant in the end, which would just cancel off. That, of course, is x cubed. Right? So we multiply this differential equation through by x cubed. Multiply dE by x cubed, and you get, well, I'm not going to actually write down what we get with multiplying by x cubed. I'm going to rely on the fact that we've designed the whole process so that what we get on the left-hand side will be d by dx of the integrating factor, x cubed in our case, times the dependent variable, which is v. The whole purpose of this, as I said, is to make sure this is what you get here. And if you apply the product rule to this, you'll see you'll get x cubed times dv dx plus 3x squared times v. Right? And that's what you'd get if you multiply this thing through by x cubed. You get x cubed here and a 3x squared v. Right? So it's basically that was undoing a product rule application. And on the other side, we get 3/2 x squared e to the x cubed. Okay, so now what we're going to do is integrate both sides. This, of course, integrates easy to just be v times x cubed. And this, well, the x squared has appeared here, so we can actually integrate 3x squared e to the x cubed is just e to the x cubed. Differentiate e to the x cubed, and you get 3x squared e to the x cubed. So integrating both sides, which we can now do. I'll put that here, I'm running out of room. Integrating gives x cubed v is, well, the factor of a half is still there, e to the x cubed plus the arbitrary constant. Remember, we must have the arbitrary constant in here. We can leave it off here, can't leave it off here. Right. Well, the only thing to be done is to just substitute back in for y, divide through by x cubed, of course, and then write down the solution. Hence, v, which is y to the 3/2 is, what do we get? 1 upon 2 x cubed e to the x cubed plus some constant over x cubed. Which we could raise to the power of 2/3 if we liked, which simplify things a bit. But sorry, I'm off the camera here. We can leave it like that if you want. Okay, that's an implicit function. That's okay for a solution of a DE. Okay. All right. So clean that off, and let's have a look at the next problem. Now this next problem is a word problem involving modelling. And what I've done here is I've not written the whole thing out, basically because I'd have to sort of pause for 5 minutes while people read it. If anybody is watching this not live, then pause the video or zip past all this cleaning business and have a read of what it says. What I'm going to do is I will read out what it says. I'll just put up basically a diagram that models what's happening. So the question says we've got a tank containing 100 litres of pure water and 2 pipes carrying salt water into the tank, one from a reservoir called A, there's a salt concentration of 4 grams per litre, and one from a tank B that has salt concentration of 1 gram per litre. The combined flow rate from both reservoirs is always a constant 1 litre a minute, although there's a valve here that can control the proportion of what's gone in. From A and B, so we've got that control over which, how much of A and how much of B goes in. But it's always 1 litre a minute coming out. Now there's an outflow that ensures that the volume of liquid in the main tank is always 100, so that must mean, of course, that 1 litre a minute is coming out of this tank. The tank is continuously stirred and well mixed. That's just a standard simplification assumption. Otherwise we couldn't be able to do it, and I've indicated that by putting a little symbol for a stirrer in there. So if we denote the flow rate coming from reservoir A by P, P litres per minute, T is the time measured in minutes, X of T is the concentration of salt in grams per litre in the tank. Now always be careful with these to make sure you match up all the units, so that if some part of the question is in hours and some part in minutes, make sure you sort out the problem there. But everything here is quite clean. Okay. Right, so that's our setup, right, and that's the diagram we've got here. Now part A says, again I've shortened what I've written here, says by considering the rates of inflow and outflow of salt, we know that little x of t, the concentration, must obey a differential equation of this shape, and there's a slight mistake there, I'll just correct. dx dt is a plus b times x, it should be here, where x of 0 is c. It's meant to be an x. Right. So that's a linear differential equation again. And the game is to find constants a, b and c. Right. And then we're asked to solve this initial value problem, and the last part is asks us to look at what do we do with the control valve to make sure we have a particular concentration in the tank at the end. Now, as is usual with these questions involving a solid dissolved in a liquid, it's almost invariably easier to do everything in terms of amount of solid rather than concentration. The question's worded for concentration, but I'm going to solve it by looking at the amount, because the concentration is just the amount divided by the total volume. So I'm going to introduce a new variable, and I'm going to use a capital X. So let's let capital X of t be the amount of salt in Now what's it called? Is it called the tank or a reservoir? In the tank, A and B are the reservoir. In the tank, at time t, measured in grams. All right. And I'm going to use a symbol. I'm going to use a big capital V, which is to be 100, be the volume of liquid, brine of course, in the tank. Right? It's a constant. Right? It's 100 litres naturally. All right. Then it follows that the little x of the question is just big X over V. Well, big X is little x times V, whichever one is convenient at the time. All right. So what we now want to do is to look at the, as the question suggests, the inflow and outflow of salt. And typically the rate of change of amount is the amount coming in minus the amount going out. It always is for these questions. The rate of inflow of salt is, well, we've got p litres per minute of coming out of reservoir A, and the concentration there is 4 grams per litre, so that must be 4 times p grams of salt coming in from 4 times p grams of salt coming in from A. And obviously the inflow rate from B must be 1 minus P, because the total flow out is from the 2 reservoirs is 1, and it's 1 gram a litre, so we'll have 1 minus P grams of salt coming from B. Which of course is 3P minus 1 grams per minute. What's the rate of outflow? So the outflow rate of salt is, well, we've got a total of X grams of salt in the tank. We assume perfect mixing, so the concentration of salt in there is X over V. 1 litre a minute is coming out, so it must be X over V amount of salt, X over V grams of salt coming out per minute. It's, the total amount divided by the volume, which in fact is the same as little x, of course, grams per minute. Okay, so the big X by dt is the inflow minus the outflow, 3p minus 1 minus x over v. Which we can see is a linear differential equation. It's not the one we were asked for. We were asked for the differential equation for little x. We've got a formula here, little x is big X over v, so we can just, or big X is little x times v, perhaps more useful here. So as big X is little x times v, this gives, well, the big X by dt, and v is a constant, remember, is going to be big V times the little x by dt is 3p minus 1 minus x over v is little x, i.e. dx dt 3p minus 1 over v minus x over v. So we got it in exactly the shape that we were told we would get, and we can now compare it to the shape that we're told. Hence, A is 3p minus 1 over v, B is minus 1 over v, and the last thing we need to know is what's the concentration of salt initially. Well, the question tells us that the tank initially contains 100 litres of pure water, so that means there's no salt, so it must be that big X of 0 is 0, and so little x of 0 has to be 0 as well. So as big X of 0 equals 0, little x of 0, which is C, is also 0. So that's given us the 3 constants we want, A, B and C. All right. So now I'll write these down over here so we have them to reference, and we'll have to clean this off. We'll do the solution of the IBP. So we've got A 3p minus 1 over B. B is minus 1 over B. C equals 0. The B, remember, is 100. Okay.
Okay. All this?
All of it, yep. Actually, A is 3p, 3p plus 1, is it? Yes, it's 3p plus 1. I've written 3p minus 1, my apologies. It's 3p plus 1 is what A is. Right. Now, I'm actually going to solve the differential equation just in the shape that was given in the question, right? As A plus bx. I'm not going to and I'll put in the actual values later on when I need them. The advantage of this is, of course, that if I've got these wrong, and then I later come back to fix it, I don't have to do very much work. And the other point, of course, of the way the question has been written is that if you can't actually work out what A, B, and C are, you can at least do this bit. Make sure this is properly dry. Well, the D is linear again, so it's an integrating factor job. So the DE is linear. And writing it in its standard form, dx dt minus bx is A. Right? With x of 0 being 0, I mean I will use 0 rather than C, obviously. Integrating factor, which we'll abbreviate to IF, as is traditional, is again x of the integral of minus b dt, which is just going to be e to the minus b times t. And as in the previous question, we don't put the arbitrary constant in there. Multiply through. The differential equation through by e to the minus bt, and we get, well, it's the same trick as before. The whole point of the integrating factor is to make the left hand side d by dt of integrating factor times dependent variable, so we're going to get that. So rather than write down an extra line, we'll just leap straight to what we know. Let's put it here. D by dt of x e to the minus bt should be a e to the minus bt. All right. Now we just need to integrate both sides of that. That side's easy because it's a total derivative. That side's just a straightforward integral, straightforward exponential. So integrating we get x e to the minus bt is minus a over b e to the minus bt plus the arbitrary constant. Well, I better not call it c because I'd get confused with the little c that we've got earlier, so I'll use capital A. Use any symbol you like, basically. Seems to be that capital A is the logical one to use here. Right. So that's the general solution to the differential equation. We could divide through, or multiply through, I should say, by e to the bt, and then put in the initial conditions, but we might as well put the initial condition in now. Usual good policy is to put the initial condition in as soon as you've got the general solution, which is what I have here. So as, put it over here, little x of 0 equals 0, we have, well, 0 times anything is 0, e to the minus 0 is 1, so it equals minus a over b plus big A. In other words, this arbitrary constant is not arbitrary because its initial value problem is a over b. And our solution, make sure we get all these minus signs in the right order. X, hence X is A over B into, when we divide it through, we're going to get an e to the bt minus 1. And if we now put in our values for A and B, A over B, well, the 1 upon B's cancel themselves off conveniently, and we're going to get A over B is actually negative, it's minus 3p plus 1, so that's 3p plus 1, flip those over the other way around, 1 minus, and B is negative, so it's e to the minus t over b, or t over 100 if you want. I suppose I should write it as t over 100, because that's what's actually listed in the question. V is not part of the question. Usually you don't introduce new symbols in your answer. Okay? So that's what we've got. And that's a minus t, of course. Minus 2. That's the solution of our initial value problem. Yep. Now Vico's got room to do C here, possibly just. Well, the last part says, what value should P take in order for the outflowing concentration of salt to be 2 grams per litre as T goes to infinity? Well, as T goes to infinity, this term, e to the minus t over 100, that term will disappear, so we'll just be left with 3p plus 1. So the limit as t goes to infinity, x of t, is just 3p plus 1, right, because the exponential term disappears. So what we'd expect from on physical grounds, you'd expect if you leave the valve shut, eventually the concentration is going to settle down to something, and this is 2 if and only if P is, well, 3p plus 1 must be 2, so P has to be a third. So in order to have your limiting concentration of salt to be 2 grams per litre, you must have a third of a litre coming from A and 2/3 coming from B. All right. Any questions on that from the... No? Good. Okay, so clean it off and go on to the next one. Thank you, Catherine.
Mm-hmm. So I've just realised there was a typo, a small typo in one of my answers, but I might wait until John's finished his question and then tell at the very end.
Okay.
Yeah.
Do you want to do it now while you remember?
No, I think I should. I'll still remember. You can guess which question, which sub-question it was in.
Yes. Special prize of a pat on the back for anybody who gets it before the end.
Yeah, type in with your answers.
Now this is another question where I've actually reworded the question here. The question in the problem in the exam is a little longer, but I've got the essence of it here. What we've got is an engineer who wants to know a value for the integral from 0 to 1 tan inverse of sine of x. And the question in the exam says, well, she puts this into Maple, as anybody sensible would do, and gets it's a total mess, right? It's almost impossible to make sense of what Maple is doing. I mean, I did this when we set the question, and it just doesn't quite work. So what she decides to do instead is to take a Taylor series for the function tan inverse of sine of x, which she gets at a Maple, integrate that, and then use that as an approximation, just truncate the series at some point. Because the other advantage of doing this is that with a series approximation, you can actually say something about your error. Whereas if you just have to have the number out to Maple, it's a bit hard to say exactly what the error is. I think that's all the details of the question. Let me just see if there's anything else in the question I should have said. All right. No. All right. So the engineer puts in series arctan of sine of x. Remember, Maple has to use arctan to this, and asks, well, she asks the series about x equals 0, so that's a series in powers of x, it's the Maclaurin series, up to the term involving x to the 11, which if you don't put that number in, it gives you 5, I think, as a default. So Presumably she did that and thought, well, that's not enough, let me put another number in here. Right. And this is the thing that comes out. X minus half x cubed plus 3/8 x to the fifth minus, and then lots of really more annoying terms. Right. Obviously we don't expect you to check that. The question didn't say that, but none of you will be daft enough to try and do this. And the question then says, well, use a maple output to find the first 4 non-zero terms in the series approximation for integral 0 to 1 tan inverse of sine. The question actually says the first 4 non-zero terms, which I've not said, but it refers to it as a Taylor series. Well, technically it's not a Taylor series because this is a number, not a function, but we just meant use the Taylor series to find the approximation. It would really be a Taylor series for the integral from 0 to t of tan inverse of sine of x dx, but rather than get involved in that, I've just simplified it to say find a series approximation. All right. And the whole point of this exercise is that power series behave like they're infinitely big polynomials. You can just integrate and differentiate them term by term as well as add and subtract them if you want. In this case, we're going to just integrate this term by term, and that will give us a series for the sort of the function 0 to an arbitrary number. So part A, how do we want to say this? The integral from 0 to, well, let's call it 0 to x tan inverse sine of t dt. Right, change the dummy variable, of course. Well, let's put some words around this. Let's say as. We just need to integrate this series that Maple has given us and do it term by term. We'll integrate x, and we're going to get x squared on 2. Integrate half x cubed, we're going to get 1 on 8 x to the 4. Integrate 3/8 x to the 5, we're going to get 3 over 8 by 6 x to the 6. Right. Minus, what's that number again? 83 over 240. Well, we only need the first 4 terms, so I'll not need that last term here. X to the 8 on the denominator, x to the power of 8 plus etc. There's more terms obviously. The next term would be 8375 over 24190 x to the 10. In fact, we don't need that. Okay. That's just using the properties of Taylor series. Now we just put x equals 1. We have the integral from 0 to 1 tan inverse sine of t dt is 1/2 minus an eighth plus 3 over, no, not 3 over, let's get rid of that, cancel the 3's off, get a 16th, right, put the x equal to 1 in here, minus, we want the first 4 terms, 83 over 8 times 240, which is 1920. So it's approximately that. Right. That's the first 4 terms in a series approximating this number. Yep. Now, part B says use the first 3 terms of your answer to A to find a rational approximation to this particular number. So the first 3 terms will be just a half minus an eighth plus a 16th. So a rational approximation to this integral. I'm flipping between t and x as the dummy variable. That shouldn't bother anybody. So half minus an eighth plus a 16th. Well, that's put everything over 16. I suppose that's 8 minus 2 plus 1. 9 over 16. 7 over 16, sorry. 9, yes, 7 over 16. Okay. And our last part, assuming the series is alternating, it certainly looks alternating. It is in fact alternating, by the way, if you actually do the work to find this. But assuming that, estimate the error in B. Now, the point here is we're using the theorem that says that if you've got an alternating series, then the error in truncating at the nth term is bounded above by the next term. So the error in this is bounded above by whatever the next term in the series is, which in our case is 83 over 1920. That's just a straight application of a theorem from the lecture note. So let's just write that down. The error is less than or equal to the next term. Sorry, let me start writing a little larger, I'm writing smaller. The next term, i.e., is less than or equal to 83 over 1920. Now, you're not asked to put that in decimals or anything like that, but if you did want to, I mean, it's the absolute value. I mean, you forget the sign here always when you're estimating error. That is approximately, I got my calculator out, that's approximately 0.043. Right. Now, I did get Maple to give me a numerical approximation of this to 10 figures and compared it to 7/16, and the actual error is 0.02 something or other. 0.024 in fact what I've got here. So that's definitely an upper bound on the error. Okay. So 7/16 is actually a better approximation than it looks at first sight, but that's typical. Error approximation is always an overestimate. Okay. I think that's it for that one.
Excellent.
Any questions coming from? No. Okay. I'm just trying to find my notes for this part here because it gets a bit confusing. 4, 5, 3, 2, 9. I seem to have lost my notes for this one. Doesn't matter too much. So this is an example of applying surface area width. The question doesn't say that. I've not written this down here, but the question in the exam paper did say, do not do the integration. So you just asked, thank you, Catherine. Yes, okay. We're not actually asked to do the integration to find the surface, which is just as well because it's actually quite complicated. We just have to actually write down the integral. I mean, as you possibly all know, actually finding surface areas in this sort of way and finding arc lengths, typically very difficult. Very hard to cook up a question that gives you something you can actually do. But what we want to do is what we know is the surface area. Let's write down the general formula. The surface area is the integral between our two limits, in our case 1 to 2 pi times y of x times the square root of 1 plus dy dx all squared dx. Okay, that's our general formula applied to the case between our two limits. So what we've got to do is find dy dx, square it and add 1. And then just write the thing down. Okay. Technically that you might think, well, isn't that the answer to the question? Well, I suppose it is, but of course you wouldn't get full marks for it. We are expecting you to do a bit more than just write the formula down. Okay. So let's do this. Dy dx is just going to be 3x squared upon 2 plus 1 upon 6x squared. Right. And then when we square that and add, one plus dy dx all squared is 1 plus. Well, it's tempting to sort of pull out the factor of x squared and play about, or 1 over x squared I should say, and play about with it, but let's just square and leave it as it is. You're going to get 9 quarters x to the 4th plus, well, happily there's some cancellation off there. The x squareds cancel off 3s, we should get a half out of this, plus 1 on 36 x to the 4th. And there's not in fact anything we can do with that. Right? We can't rewrite that as a square with the extra 1 here. In fact, I realised in preparing this, if the question had had a plus sign here, so it would be an x squared plus 1 upon 6, that would have been a minus sign, that would have been a minus a half, we'd have actually got a perfect square here. So we could actually have then, taken that square root. It just illustrates what I said earlier, that actually being able to write these examples down where you can actually do the integration is quite hard. Okay. I suspect the person who sent the question, which might have been me by the way, just got the minus sign wrong in doing the calculations, and nobody bothered picking it up because the question doesn't change. I mean, it's the same question, and we're not asking you to do the integration after all. Right. Anyway, enough waffling. Let me just point out that's 9 over 4 x to the 4 plus 3 halves plus 1 on 36 x to the 4th. So the area is the integral from 1 to 2 pi times that thing there. Well, you might go take the 2 in, I suppose. Pi into x cubed minus 1 upon 3x times that thing there, 9 quarters x to the 4th plus 3 halves plus 1 on 36 x to the 4th whole to the half dx. And that's all we're asked for. We're not asked to actually do this integration, basically because we can't. Right? This is a possible integral to do, basically. That's all we're asked for. Okay. That's that one.
Final part.
Final one.
Mm-hmm. There you go.
Now, earlier Catherine complained about a discrete mathematician being asked to do some calculus. Here we've got somebody, a calculus lecturer, being asked to do something that sort of impinges on number theory, but not really that heavily. So inventing a new sequence. This is a summation of sequences. A sequence, I don't know if this is my pen, I just picked up. No, that was it. Pn, for n bigger than or equal to 2, it denotes the number of positive integers, obviously, less than or equal to n that are prime. So this is a prime counting function. And the question gave you an example. P of 5 is 3, because 2, 3 and 5 are primes less than or equal to 5. P of 6 is 3 as well, because there aren't any more primes. P of 7 is 4, and so on. And the question asks, do either of these two series converge? So we're summing from 3 to infinity 1 upon p to the n, and summing from 3 to infinity minus 1 to the n over p to the n, pn. We're summing from 3. Where we start the sum from, of course, doesn't make any difference to convergence and divergence. The sequence isn't defined for p less than 2, but we're avoiding that point. It doesn't make any difference. Well, this is the last part of the last question, and it's designed, as is usual, to make you have a bit of a think here. But in fact, it's not actually that hard if you make the one observation that you need to do. Let's actually write down some values of Pn, just to get us a feeling of what's going on. Here's n and here's Pn, starting from 2, 3, 4, 5, 6, 7, 8. That would be enough. No, we'll have one more. 2 more maybe. 3 more. Well, P of n, how many numbers less than or equal to 2 are prime? Well, there's only one of them, of course. 2 and 3 are both prime. There aren't any more here. We've already told that P of 5 is 3. As I mentioned, P of 6 is 3. 7, well, 2, 3, 5 and 7. That goes up to 4. 8's not prime. 9's not prime. 10's not prime. So this sequence only increases when we hit a prime. And 11, 5, and so on. Okay. And from this little table, two things should be obvious if they weren't obvious to you before. The first is that Pn is an increasing function, right? And secondly, that it's always less than or equal to n. And the reason we know that Pn is less than or equal to n is that not all numbers are prime. And that's all we need as a observation, as not all integers are prime. P of n is less than or equal to n for every n. Right. So when we're summing this first series, sigma 1 upon p to the n, we're adding a 1 plus 1 plus a half plus a half plus a third plus a third plus a quarter plus a quarter plus a quarter, and so on and so on. In particular, we're adding up numbers when we take the reciprocals that are always bigger than 1 upon n. So it follows that 1 upon Pn is bigger than or equal to 1 upon n for all n, or all n bigger than or equal to 2 at least. It's only defined there. Got a problem coming up?
Bigger than or equal to 3, perhaps?
Well, it doesn't matter whether we start at 2 or 3. Yeah, it is the sum says 3, but it is indeed, I'll put a bigger than or equal to sign because it's actually equal at, in fact it's always strictly bigger than, but again it doesn't matter too much. Now what we know is that if we sum 1 upon n, that's the harmonic series, and the harmonic series diverges. Sigma 1 upon n diverges, and 1 upon Pn is a sequence of bigger numbers, so that must diverge too. And that's the comparison test. As the sum from n is, well, we might as well start at 3, doesn't make any difference. 1 upon n diverges by the comparison test sigma 1 upon p to the n diverges. Okay. So the first series we've got here diverges. Okay. What about this here? What about the alternating sum minus 1 to the n over p to the n? Well, that's where we need the other observation I've got here, which is that this sequence is clearly monotonic. Right? So Pn is clearly, Pn plus 1 is bigger than or equal to Pn, because you're only ever going to get more primes. Right? If you have a prime, you've gone up by 1. If it's not a prime, you haven't. So we know that Pn plus 1 is bigger than or equal to Pn for all n. Clearly they're always positive. You might see what I'm getting to here. All Pn greater than or equal to 0. And, well, this is a fact that's not in the question, but I would really expect you to know, is that there are infinitely many primes. So Pn is going to tend to infinity as n goes to infinity. So that's not part of the problem, not part of the statement, but it is something we would expect you to know. Right? There are infinitely many primes. And if Pn is going to infinity, 1 upon Pn must tend to 0. Hence, 1 upon Pn is monotonically decreasing, all right, always going downwards, monotonically decreasing to 0, right, because Pn is tending to infinity, and it's positive terms, as I just said, so it follows from the Leibniz test that this alternating series must in fact converge. So hence, by the Leibniz test or the alternating series test, that's the correct spelling of Leibniz, doesn't matter, hence by the Leibniz test, sigma minus 1 to the n, so Pn converges. Converges conditionally, right, because the sigma 1 upon Pn didn't converge, it diverged. Okay, I think that's it.
Yeah, that's it for your
All right,
question.
so that's it for the question, and now
I just like to
reveal the big
correct
secret.
my...
What is Catherine's error?
yeah,
What is the
so
secret?
guess where this was? Of course it was in the thing where I had to integrate a continuous function, wasn't it? So this is question 3, part 4, part B. And we made a change of variables. We were proving that the second moment was infinite, and we were staring at this integral, remember, from 1 to infinity of a constant x over 1 plus x squared dx. We made a change of variables, and we discussed that, and we said y should be 1 plus x squared, and we talked about the fact that dy on 2 was x dx. Dy by dx was 2x, yes, we talked about that. What I didn't get right was you also have to change where you start from. So if x is 1, y is 2. So this integral is actually equal to the, well, c on 2 outside. The integral starts at 2 and goes up to infinity dy dx, dy on y, sorry. So I think that when I did it live, I had 2 goes at this. I think first I put a 0 and we realised that wasn't right. Change it to a 1, but it actually should have changed to a 2 because when x is 1, y is 2. So that was the typo. Please correct that in your notes, okay?
Still the integral is still infinite, though.
The integral is still infinite. I'd also like to say, if you don't know that proof that there are infinitely many primes, Google it because it's lovely and it's from the ancient Greeks, I think.
There are hundreds and hundreds of different proofs. The
Yeah.
simplest one.
The simplest one is the ancient
That
Greek
I was
one.
going to say, if you weren't sure that you could actually assume this, then those of you who knew a proof could put it in. But I'm pretty certain that we
I'm
would
sure
just
that
accept
they
it
would
as a
accept
statement.
that, yeah.
Okay.
So I think we're done. Thanks
so.
very much to Josh, who has given us technical support. Thank you, John.
Thank you, Catherine.
And good luck in your exams. Bye.